discrepancy between the specified service voltage and the voltage requirements of the condensers can arise for several reasons. Firstly, the mechanical schedule might contain incorrect information. The schedule could be outdated or copied from a project with different voltage demands. Secondly, a voltage conversion transformer may be planned or already installed to convert the 120/240 volt service to 208 volts specifically for the condensers. Thirdly, the condensers could be supplied by a completely separate 208 volt service, while the rest of the building utilizes the 120/240 volt service. Fourthly, errors in interpretation of the service specifications or mechanical schedules are also possible. To clarify this discrepancy, several steps should be taken. Firstly, contact the engineer responsible for the prints to confirm the voltage requirements for the condensers and inquire about any planned voltage conversion systems. Secondly, carefully review the electrical plans to look for notes or details indicating a voltage conversion setup or a separate service for the condensers. Thirdly, consult with a licensed electrician who has experience with commercial buildings. A qualified electrician can help determine the correct voltage needs for the condensers and recommend any necessary voltage conversion devices. When preparing a bid, you must take into consideration these factors. Firstly, verify that the voltage specified in your bid accurately matches the actual voltage requirements of the condensers. Secondly, if a voltage conversion is necessary, include the cost of the appropriate equipment and its installation in your bid. Thirdly, clearly state any assumptions or clarifications you have made regarding the voltage requirements to avoid potential misunderstandings later. Understanding the voltage requirements is important for ensuring the correct operation of the electrical equipment and preventing damage. In situations where there is a discrepancy between the service voltage and the equipment voltage, it is crucial to investigate the possible causes and take steps to clarify the requirements. Incorrect schedules, voltage conversion, separate condenser service, and errors in interpretation are potential reasons for such a discrepancy. By contacting the engineer, reviewing the electrical plans, and consulting with a licensed electrician, you can gain a clearer understanding of the voltage requirements and any planned voltage conversion systems. When preparing a bid, verify the voltage requirements, include the cost of voltage conversion if necessary, and clarify any assumptions to avoid misunderstandings. Remember that electrical systems must adhere to the National Electrical Code, and voltage conversions require careful planning and execution to ensure safe and reliable operation. The NEC addresses voltage requirements and conductor sizing in articles like 210.19 and 215.2. Furthermore, the NEC mandates proper overcurrent protection as outlined in Article 240.4, safeguarding the electrical system from overloads and short circuits. Grounding and bonding are also crucial for safety, as detailed in Article 250.4, ensuring a low impedance path for fault currents. Regarding voltage drop, the NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders, as highlighted in the informational notes within Articles 210.19 and 215.2. These recommendations help maintain optimal performance of electrical equipment. When performing voltage conversions, it is important to select appropriate transformers that meet the voltage and capacity requirements. Transformers should be installed in accordance with NEC Article 450.3, ensuring proper ventilation and clearances. Additionally, wiring methods must comply with NEC Chapter 3, using suitable conductors and raceways for the specific application. When dealing with electrical systems, it is essential to adhere to the relevant codes and standards to ensure safety and prevent damage. The NEC provides comprehensive guidelines for electrical installations, covering various aspects such as wiring methods, overcurrent protection, grounding, and voltage drop. Consulting with a licensed electrician and following the NEC requirements are crucial steps in ensuring a safe and reliable electrical system. In summary, discrepancies between service voltage and equipment voltage can arise due to incorrect schedules, voltage conversion, separate condenser service, or errors in interpretation. To clarify the requirements, contact the engineer, review the electrical plans, and consult with a licensed electrician. When bidding, verify the voltage requirements, include the cost of voltage conversion if needed, and clarify assumptions. Ensure compliance with the NEC and relevant codes and standards to ensure a safe and reliable electrical system. Remember, proper planning and execution are key to successful electrical installations. When converting voltage from 120/240 volts to 208 volts, consider the transformer kVA rating. To calculate the required kVA, determine the total power and watts needed by the 208 volts loads and divide by 1000. Then, divide this result by the power factor, which is typically around 0.8 for inductive loads like motors. For example, if the total power of the 208 volts loads is 10,000 watts, the kVA would be 10,000/1000/0.8 equals 12.5 kVA. So you would need a transformer with a kVA rating of at least 12.5 kVA. Also, when selecting the transformer, ensure it is designed for continuous operation and has adequate overload protection. In addition to the transformer, consider the wiring and overcurrent protection for the 208 volt circuit. Size the conductors according to NEC table 310.16 based on the ampacity of the circuit. The overcurrent protection should not exceed the ampacity of the conductors as per NEC section 240.4. Also, consider the voltage drop in the circuit. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Use the voltage drop formula to calculate the voltage drop in the circuit and adjust the conductor size accordingly if needed. When installing the transformer, follow the manufacturer's instructions in NEC Article 450.3, which covers transformer installation requirements. Ensure proper ventilation and clearances around the transformer. Also, provide a disconnecting means for the transformer as required by NEC section 450.14. The disconnecting means should be readily accessible and capable of disconnecting the transformer from the power source. Finally, remember to ground the transformer and the 208 volt circuit properly, in accordance with NEC Article 250. Grounding ensures a low impedance path for fault currents and helps protect against electric shock. Use a grounding electrode conductor of the appropriate size, as determined by NEC Table 250.66, and connect it to a grounding electrode system that meets the requirements of NEC Sections 250.50 through 250.58. In summary, when dealing with voltage conversion from 120/240 volts to 208 volts, consider the transformer kVA rating, wiring and overcurrent protection, voltage drop, transformer installation requirements, disconnecting means, and grounding. Always follow the manufacturer's instructions in the NEC to ensure a safe and reliable electrical system. When you have a 120/240 volts single-phase service and need 208 volts for specific equipment, the most common solution is to use a step-up transformer. This transformer takes the available 240 volts and converts it to 208 volts, providing the necessary voltage for the condensers. The transformer size is crucial and depends on the total load of the 208 volts equipment. To determine the correct transformer size, calculate the total volt amps VA required by all the 208 volts loads. Add up the VA of each condenser, taking into account their individual power consumption. Once you have the total VA, divide it by the input voltage 240 volts to find the required current on the primary side of the transformer. The transformer should be rated to handle this current continuously. It's also a good practice to add a safety factor of 25% to the transformer size to account for future expansion or unexpected loads. This ensures that the transformer won't be overloaded and can handle any additional demand. Next, you need to consider the wiring and overcurrent protection for both the primary and secondary sides of the transformer. The conductors on the primary side should be sized according to the calculated current and the NEC guidelines. Table 310.16 provides the ampacity of conductors based on their size and insulation type. The overcurrent protection device, such as a circuit breaker or fuse, should be sized to protect the conductors from overload. On the secondary side of the transformer, the conductors should be sized based on the output current of the transformer. Calculate the output current by dividing the transformer's VA rating by the output voltage 208 volts. Again, use table 310.16 to determine the appropriate conductor size. The overcurrent protection device on the secondary side should be sized to protect the conductors and the 208 volts equipment. Remember to properly ground the transformer and the 208 volt circuit. Grounding provides a path for fault current to flow back to the source, which helps to protect against electric shock and equipment damage. Follow the NEC guidelines for grounding transformers, which can be found in Article 250. Make sure to use a grounding electrode conductor of the appropriate size, as determined by Table 250.66. It is also important to consider the location and installation of the transformer. The transformer should be installed in a dry, well-ventilated area, away from combustible materials. Follow the manufacturer's instructions for installation and mounting. Provide adequate clearance around the transformer for ventilation and maintenance. In summary, to provide 208 volts for condensers from a 120/240 volt service, use a step-up transformer. Size the transformer based on the total VA of the 208 volts loads, and add a safety factor. Size the wiring and overcurrent protection for both the primary and secondary sides of the transformer according to the NEC guidelines. Properly ground the transformer and the 208 volt circuit. Install the transformer in a dry, well-ventilated area, following the manufacturer's instructions. Always consult with a qualified electrician to ensure that the installation is safe and compliant with all applicable codes and regulations. The NEC is a comprehensive document, and it is essential to have a thorough understanding of its requirements before working on any electrical system. If you are not familiar with the NEC, it is best to leave the work to a qualified electrician. They have the knowledge and experience to ensure that the installation is done safely and correctly. The 120/240 volt single-phase service is a common configuration for residential and small commercial buildings in North America. The 120 volts is used for lighting, receptacles, and small appliances, while the 240 volts is used for larger appliances such as electric ranges, dryers, and air conditioners. The 208 volts is a three-phase voltage that is typically used in commercial and industrial buildings. It is derived from a 208Y/120 volts three-phase system, which is a common distribution system in North America. The 208 volts is often used for motors, HVAC equipment, and other heavy-duty equipment. When you have a 120/240 volts single-phase service and need 208 volts for specific equipment, you have a couple of options. One option is to install a step-up transformer, as discussed earlier. Another option is to install a phase converter. A phase converter is a device that converts single-phase power to three-phase power. There are two main types of phase converters: rotary phase converters and static phase converters. Rotary phase converters use a motor and generator to convert the single-phase power to three-phase power. They provide a balanced three-phase output and can handle heavy loads. Static phase converters use capacitors and other electronic components to convert the single-phase power to three-phase power. They are less expensive than rotary phase converters but may not provide as balanced of an output. If you are considering using a phase converter, it is important to choose the right type and size for your application. Consult with a qualified electrician or electrical engineer to determine the best solution for your needs. In addition to the technical aspects of providing 208 volts for the condensers, it is also important to consider the cost. Step-up transformers and phase converters can be expensive, so it is important to factor this cost into your bid. Also, remember to include the cost of the wiring, overcurrent protection, and other necessary components. When preparing your bid, be sure to clearly state any assumptions that you have made regarding the voltage requirements and the method of providing 208 volts. This will help to avoid any misunderstandings later on. In conclusion, discrepancies between service voltage and equipment voltage can arise due to incorrect schedules, voltage conversion, separate condenser service, or errors in interpretation. To clarify the requirements, contact the engineer, review the electrical plans, and consult with a licensed electrician. When bidding, verify the voltage requirements, include the cost of voltage conversion if needed, and clarify assumptions. Ensure compliance with the NEC and relevant codes and standards to ensure a safe and reliable electrical system. Remember, proper planning and execution are key to successful electrical installations. Always consult with a qualified electrician to ensure that the installation is safe and compliant with all applicable codes and regulations.